In this video, we're going to look at trends in the periodic table, and we'll look at some of the patterns that exist in the periodic table according to their trends. So the first trend we'll look at is the atomic radius. So that's the measurement from the center of the nucleus to the outermost electrons. And that increases as you move down a group. And that kind of makes sense because as you're going down a group, you're starting a new period, you're adding on another energy level. So that means that there's going to be greater distance from the outermost electrons to the nucleus. But the other thing that might not make as much sense is that it actually decreases this way. Even though you're adding more electrons as you're going this way, the number of protons are increasing as you move across. So the electrons don't change energy levels as you're moving this way. So the more protons you have in the nucleus, the more pull there will be from the protons on the electrons in the orbits. So that will pull them towards the nucleus. So if you're looking at atomic radius across the periodic table, it would increase going left and increase going down. Now the pattern with ionic radius is slightly different. So metals lose electrons to become cations, so positive ions, and non-metals gain electrons to become anions. And those ions, the ones below, are isoelectronic, which means that they have different atomic numbers, but they have the same number of electrons as each other, and as neon. Remember, electrons are trying to either fill up or empty their outermost valence shell to become closest to their neighboring noble gas. So in this case, the ionic radius increases as the number of protons decreases. So in this example, aluminum 3 plus is smaller than magnesium 2 plus. So magnesium 2 plus actually has fewer protons, and then sodium 1 plus has one fewer protons than magnesium. And then we jump back up to the next row. So then neon would be right here. Fluorine would be bigger than sodium. The fluoride ion, the oxide ion would be bigger than fluoride, and then the nitride ion would be bigger than the oxide ion. So this one works a little bit trickier than the typical ones. So if you were to look at the number of protons, this has 7, this has 8, this has 9. Neon would be here. It has 10, 11, 12, 13. So ionic radius increases as the number of protons decreases, as is demonstrated in this example. So this is a graphical representation for the ions of period 3. So it goes just like this. So sodium is smaller than magnesium, is larger than magnesium, which is larger than aluminum, which is larger than silicone. But then there's a jump because these ones are going to be isoelectronic to argon, so they're larger than these ones. These ones are isoelectronic to neon, if you remember. So the first ionization energy is the amount of energy that's needed to remove one electron from the atom, so the very first electron from the atom. And the rule for this one is that it decreases as you move down a group, so it increases as you're moving up the group. And the reason why is the atomic size is larger when you're going down the group, so this would be weaker. And the valence electrons are farther from the nucleus, so the pull on the electrons from the nucleus is lower, so it's going to be easier to pull electrons off from these ones. You have fewer and fewer energy levels as you move up, so it's going to be harder and harder to pull the electrons away because the positive pull from the nucleus is closer than down here. Then it also increases as you move across a period. So the reason for this is the attraction between the nucleus and the electrons is increasing due to the increasing number of protons in the nucleus. So as you get more and more protons, there's a stronger positive pull, so it's going to be harder and harder to pull electrons off. So that's first ionization energies trend. So the electronegativity trend says that it will increase across a period, so going this way, so greater electronegativity this way, and increase moving up the group, or decrease going down the group. And the electronegativity is the ability for an atom to attract electrons in a bond. So depending on what element it is, the number of electrons that it has in the valence will determine how strong a pull it has on other electrons on other atoms. The electronegativity difference, so we can look up on the periodic table the values of electronegativity. The difference between two atoms will help us decide the type of bond that will form. That's the delta En. We'll spend some time in a later lesson finding out what type of bond will form, but the general rule is if the electronegativity change, if the delta En is from 0 to 1.7, then it's a covalent bond. And if the delta En is greater than 1.7, it'll be an ionic bond. But like I said, we're going to spend time on figuring out the types of bonds that form in a later lesson. So electron affinity is defined as the amount of energy that's released when an electron is attached to a neutral atom. So when it becomes an ion, an anion. It can also be looked at as likelihood of an atom to become an anion. So this one increases across a period and then decreases down a group. So increases up the group and then across the period. So atoms over here are most likely to become anions. They have the strongest electron affinity, whereas the ones down here at the bottom of the group have the lowest electron affinity. So metallic behavior. So as we know, metals are malleable, and they're good conductors of heat and electricity. We've learned that in grade 9, grade 10, and again this year. But depending on where a metal is found on the periodic table, they will have different amounts of malleability and conductivity and so on. So not all metals are as metal as other metals. So in this pattern, the metallic behavior decreases as you're going across a period, so decreasing. So it increases moving towards the alkali metals, towards group 1, and then it increases as you move down a group. So the most metal metals are the ones at the bottom of the alkali metal section. So at the bottom of group 1, those would be very metallic metals. And then as you move up and across this way, less metallic. And if you think of aluminum, it's not such a great conductor and it's not as malleable as other metals. It's found up here. So it increases moving towards group 1 and then down the group. So boiling point is a little tricky as you're moving across a group, or a period, sorry. So as you're moving across the period, the structure and the bonding will change from metallic to giant covalent and then to molecular covalent. So as you're moving across the period, the metallic bond will increase, and as that's happening, the boiling point increases until you get to the metalloids, and then from the metalloids to the nonmetals, the boiling point starts to decrease. So as you're moving across, the boiling point increases till you get to the metalloids, and then it would decrease as you're going across the nonmetals. And as you know, group 18, the last group, the noble gases, they're all gases. This is just showing you the trend of boiling points across period 3. So sodium has a low boiling point, magnesium and aluminum are higher, silicon is quite high, and then there's a plunge, and you can see that phosphorus, sulfur, chlorine, and argon have low boiling points.